All right, so if you haven't already heard enough acronyms of ASR test methods, I'm going to throw one more, which probably you already heard again, but MCPT, the ASTM C1260 test, which is what I'm going to talk about is this MCPT-based approach towards evaluating ASR potential of job concrete mixtures. I'd like to acknowledge my graduate student, Vichi Wong, who was helpful, as well as my former student, Inamur Latifi, who worked on this, developing the MCPT, the ASTM C1260 method that we developed a while ago. So it would be prudent to take a look at all the different test methods that we've had in our standards and specifications to deal with ASR or ACR, alkali aggregate reactions, over all these years. You know, it's interesting that given that we've sort of figured out what ASR is in about, what, 1930, late 1930s, early 40s. It's almost 80 plus years, and we're still, this is an active area of research, and we're still doing a lot of test methods and so forth. Sort of goes to show the complexity of this problem. So as I've indicated here, a couple of test methods in the past have now been withdrawn, but still there are a number of test methods that are being, in the standards and being used, both for ASR and some for ACR, although that's a little bit of a less common problem that we face. And all of these methods are to evaluate aggregate reactivity. Right? And then there are a bunch of other methods that are variations of this method, the aggregate reactivity test, to look at or evaluate ASR mitigation measures, a number of those. So what I'm going to focus on today is actually two test methods, using one as a reference, but really the focus of it is going to be on the ASTM C1260 or the miniature concrete prism test. But I'm going to use, sort of draw your attention to a test method that has been used in the past. I don't know how much it is still used now, is the ASTM C1291 test method. That is the motor bar test with Pyrex glass as an aggregate. If there were any test methods in all of this that came a little close to evaluating job mixtures, probably C441 was one of those. Obviously 1567, 1293, these certainly you can use to evaluate binder compositions and how they mitigate ASR. But let me kind of refresh your memory a little bit with the ASTM C441 test method, what this method is, right? So this is a method where you make motor bars with different types of binders depending on what you're looking at, using Pyrex glass aggregate. Pyrex glass is a very reactive aggregate. It has actually a lot of alkalis in it. And that has been a source of problem with that test method, is that it sort of supplies its own alkalis. But typically what we require for that test is a high alkali Portland cement as a reference or a control mix. And then you typically run this test using pozzolans, about 25%, or slag at 50%. And it also, the test method also has a provision to evaluate job cementitious materials in whatever combinations, whether it's binary or ternary blends, that you end up using those. So the water to binder ratio in these motor bars is about 0.45. And essentially what you do is you cast, depending on what the intent is, you could cast up to 3 sets of specimens. You have a control mixture, just with high alkali Portland cement. You have a test mixture that has a combination of this cement with either a pozzolan or slag. And then you can also cast a job mixture that is pretty much with any Portland cement, that is the job cement, with any replacement level of pozzolan that is going to be used, right? And you measure the expansions of these motor bars, and you eventually end up determining a % reduction in expansion with reference to the control sample. And you could use that as a basis to make sure you achieve a certain level of mitigation. So sort of this is the concept. Obviously, I'm not using 441 method, but the concept of using a control mix, a a test mix or a job mix, depending on what it is, in the MCPT method, or the ASTM T380 method you probably heard earlier today. So this is, what I have there is basically a summary of how these samples are made and what the requirements in terms of mix design. So these are concrete prisms that are 2 by 2 square cross section with 11¼ inch long. Typically the coarse aggregate that is used in this is limited to about a ½ inch max size. The volume fraction of the aggregate of about 0.65 with a certain gradation requirements there. And the cement content for a control mix is typically about 420 kg per cubic meter with a cement alkali level of about a 0.9 plus or minus 0.1. And in a standard test, you boost the alkali levels to 1.25%. The water cement ratio is about a 0.45. And then it turns out that the way this method was developed, and I presume the 1293, the CPT as well, is that when you have the combination of the cement with such high alkali level with the water cement ratio, you end up with a poor solution in that test mix of about roughly a 1 normal sodium hydroxide concentration, right? So in this test, one of the significant differences between the concrete prism test and this one is, this is the test we store these samples in a soak solution that matches the pore solution, right? In this particular case, the soak solution or the storage environment is in a 1 normal sodium hydroxide solution that matches with the pore solution of the design concrete. And the storage environment is a 60 degrees centigrade. And then we monitor the expansion of these prisms over typically 56 days, in some cases up to 84 days, right? When it is the mitigation version of this test to evaluate ASR mitigation measures, everything is essentially the same. The cementitious content remains the same, but now the binder is a blend of Portland cement plus whatever pozzolans that you end up using. So this is sort of the standard test to evaluate these things. The criteria for expansion in this test, depending on if you're looking at characterizing aggregates, you have a table in the standard that tells you what the expansion should be at different points of time to characterize the reactivity of the aggregate as being either non-reactive or a slow or a low reactivity, moderate, high, or a very high reactivity aggregates. When you go to the mitigation aspect of it, the expansion thresholds are as shown. If you're typically less than 0.02% at 56 days, these are very effective, the mitigation measures. And if they're over 0.025, they are not effective. So you have to bump up your dose or something. And the sort of the gray region there between 0.02 and 0.025 is where you either have to look at some late age expansion rates to see how those curves are trending, or perhaps you have to redo this test with a higher level to meet the requirements. Now, how do we adopt a standardized test method to evaluate a job mixture? The fundamental challenge that we have with the job mixture is that the job mixture is nothing like what a standardized mixture is, right? Your water cement ratios are different, your total cementitious contents are different, the alkali loading in concrete is different, the dosage of SCMs are different, but you could control that in the test, etc. There are a whole bunch of variables that are not captured in standardized tests. And the purpose of a standardized test is to really evaluate against a set reference recipe. So that's the whole intent of a standardized test. In a job mix, you have everything that's variable. Not to mention, we hardly capture the influence of any regional temperature or moisture variations as to how the field performance of that concrete is going to be. So obviously, if you want to consider all these factors and develop a test matrix, it is going to be a huge jigsaw puzzle, right? It's really unrealistic for us to do. So what my intent here is to capture some of these variables and look at how they perform in MCPT when you change these variables and present an approach hopefully a way to look at job mixtures. So what I've done in this work is to look at the effect of water cement ratios, the total cement contents in these mixes, the total alkali loading, the dosage of SCMs, and also, what I'm simply don't have time to talk about everything, but we've looked at volume fractions of aggregates as well as blends of competing aggregates. That is, if you have a coarse aggregate and fine aggregate, both are reactive or different reactivities, how do they perform? I'm not going to get into that aspect of it here, but that's part of this whole business. So for this, and again, what I'm going to share with you is data that I've been probably collecting over the last several years, if not about 10 years or so. So I'm going to share some data that I've gathered through these years. For some specific expansion data I'm going to show, in this case we've used a high alkali cement for the standard test, but also a pozzolan that is of choice that I've used for this study to make a point on the alkali release, which has been a subject of a lot of previous talks, is a volcanic natural pozzolan. And if you notice, the sodium oxide equivalent content of this, the volcanic material is very high, about 6.5%. But again, to the point that was made earlier, the available alkalis or the alkali release from this plays a big role in how these materials perform, and you'll see that. One of the things we've done in this study is to match the soak solution composition with the pore solution composition for all of these mixed variables. And the model that we use to predict the pore solution composition is the one that was developed as part of the Sharp C1260 report by Stark and Dick Helmuth and others. The equation is there. And also what we've done for this particular study is to look at the pore solution that we've expressed from paste specimens that were prepared with these with this particular natural pozzolan, both at about a 20%, 30%. And as you can see here, the blue line that is shown on the top here, that is the control pore solution if it were diluted by about 80%, because at a 20% replacement, you'd have that much less cement. So we looked at that, and at 30% replacement, the 70% line, this orange line, would represent a dilution effect. If you look at the 20 and 30 here, as with different ages and over time, you clearly see that the natural pozzolan, even with over 6% equivalent alkalis, has substantially less alkalis compared to the control sample. In other words, it is not only not releasing alkalis, but actually is helping reduce the alkali dose in the concrete. So that's part of what we need to consider, is matching these things. For this study, what we've assumed is that we're not going to give that benefit of doubt to natural pozzolans and consider everything is going to be at a cement pore solution just to kind of be conservative. And I'll share some results on that. But the tests that we ran, this is a matrix of tests. Here we have to look at specifically the effect of water cement ratio. As you know, if you change the water cement ratio in concrete, your pore solution alkalinity is going to change as a function of the amount of water. And so in this study, we looked at a control boosted. This is the standard MCPT test with a water cement ratio of 0.45. And then 3 that are unboosted at 0.35, 4, 5, 5, 5. And the soak solution was based on the predicted source, the pore solution composition from the Sharp model that we used. And so we have the soak solution and the pore solution. They're fairly close. They're not exactly equal because the Sharp equation has a plus or minus factor. We went with the plus factor just to be conservative. And so that was one part of the study. The second part was looking at the pozzolans at 20 and 30% and matching the pore solution and the soak solution with those. And in the natural pozzolans, we did boost both at 20 and 30 and unboosted. So some of the soak solutions depended on whether it was boosted or not boosted. So I want to show you how this data looks when you change the water cement ratio with all these standard mixes, the 0.45 control boosted and the unboosted and so forth. So this is, we used, by the way, the aggregate we used was a siliceous argillite from North Carolina. It's a very well-established reactive aggregate. We've had a lot of history with it. And this is the expansion curve for that argillite aggregate. And the 0.02% here represents the effectiveness of the SEM threshold, but we just included here. The 0.45 unboosted one, so this doesn't have the extra alkali boosting. If you notice that early on, there is a little bit of lesser expansion than the boosted, but in the long term, it basically doesn't really matter. The alkali boosting doesn't seem to impact, because the cement itself has about 1% sodium oxide equivalent. So it's fairly high alkali cement to start with. But the moment you start reducing water cement ratio, this orange colored curve is a 0.35, and then 0.55 is the green one. You can see that the 0.55, obviously higher water cement ratio, your alkali, the alkalinity will be less initially. So you'll see that the expansion is slower, but over time it catches up and actually shows higher expansion, because higher water cement ratio, you have enough alkalis in the system and enough space for, it also is a diffusion issue, right? You have moisture getting in and actually creating that. But in a 0.35, because the matrix is tighter, there is the inherent strength to resist some of these expansion. You do see lesser expansion with 0.35. So there is a water cement ratio impact on the levels of expansion that you see. But at 56 days, if you look at the expansion thresholds, all of them have clearly failed. So simply using water cement ratio or is not going to really make a difference at all. If you look at pozzolan replacement levels, that is either 20 and 30% with boosted alkali levels, you'll notice that this is the control, the MCPT, standard boosted, and that is the unboosted 0.45. But the 20% natural pozzolan, even with boosted or 30%, they are significantly lower expansion. Even with, this is a natural pozzolan with over 6% alkali levels. If you do the same experiment with unboosted, that is no extra alkalis to the mix, again, these show even lesser expansions, right? Even at 84 days, which is the longest, the expansion level is significantly less than 0.02%. So you're able to capture the effectiveness of these pozzolans. Sort of, and clearly at 56 days, you can see those are significantly lower. So sort of a summary of all of these put together, you'll see that the natural pozzolans at 20 and 30%, especially the 30% ones, are significantly lower. Whether they're boosted, unboosted, doesn't matter. You're able to capture some of these trends in expansion. Now going back to that C441 test of looking at the % reduction in expansion. So what we did was we looked at the % reduction in expansion with reference to the control sample. And what we noticed is that at 7, 28, 56, and 84 days, there is a significant reduction in expansion, especially with these to the right here, the orange and yellow ones. These are your 30% boosted, unboosted, and the 20% boosted, unboosted. There are about 80 to 90+% reduction in expansion. That is a significant drop from the control. However, if you look at just the water cement ratios, 0.35, 0.55, those are all, they're not really reducing the expansion in the long term. This is one aspect of it. Simultaneously, we ran a 1293 two-year test. This is still in the works, but I wanted to show you the % reduction in expansion across the 20 and 30% natural pozzolans. This is about 65 weeks. About we still have a little bit left for the 2 years. It's about 104 weeks. But the % reduction expansion is very significant and comparable to what we are seeing with the MCPT. The other aspect of this, what we ran was looking at both the cement content in these mixes as well as the alkali loading. So just to get a spread of data, we looked at a low alkali cement with a 0.49% sodium oxide equivalent. We looked at 3 different cement contents in the concrete formulations from 600, 700, 800 pounds per cubic yard that led to a alkali loading about a little over, about close to 3% to about close to 4%. And then we did the same thing with the high alkali cement where we boosted it and we got a alkali loading from 7.5 to 10%. So we have a range of alkali loadings and there are 56-day expansions here. So if I were to plot this data, this is what we saw. The expansion curve of the high alkali cement clearly above the thresholds. The low alkali, they also failed because just the alkali content of cement is not just enough. It is the amount of total cement or the alkali loading in the concrete that is more important. So if you look at these in terms of the cement content versus the 56-day expansion, the low alkali ones are down below, the high alkali ones are up there. If you put both of these together, this is what you get. This is the total alkali loading in concrete versus the expansion at 56 days. You'll see that there is a very linear relationship here across the entire range of alkali content. So what is really critical in ASR mitigation is reducing the alkali loading significantly. And if you look at these numbers, this is typically less than about 5 pounds per cubic yard. You're sort of reaching lower levels. This is very much in tune with what we know already from previous experience with limiting alkali loadings in concrete. So how do we apply all of this to the job mixture? I wanted to share actually a case study that I was able to run this concept with some airfield pavements that I worked a few years ago that exhibited premature distress due to ASR. And so what we did was we prepared MCPT mixtures and we sort of went through this process with these where we matched the pour solution with the soak solution, right? And so the 2 job mixtures, I'm going to call these as these are Taxiway Tango and Taxiway Victor. These were from the same airfield pavement. We probably wouldn't do this at this time, but this was a pavement that was built some time ago when the specifications were still light, especially on the FAA side for ASR. And they used a type 1 cement with the alkali content shown there. This is a class C fly ash with about a 15% dosage. Clearly, we know that that would not work, but that's what they ended up using. The Victor was actually a 40% slag dosage. And this is the recipe for the mixes, both the mixes. And so what we did was we took this mix design data and we ran a bunch of MCPT tests. So the blue curve here represents the standard MCPT test with the aggregate. And the other 2 represent the Tango mix with the job mix of 15% fly ash and the green is the control with the straight cement. And what we find is that the aggregate is clearly reactive if you run the standard MCPT. If we run the Tango mix design with the 15% C ash and the straight cement, clearly the C ash was not effective, and you can see that at 56 days, clearly they're above the threshold, so they fail. When we ran the same exact batch of tests on this Victor Taxiway mix, this had a 40% slag. You can see that the aggregate was reactive by itself in the standard MCPT. If we did with 100% cement with that particular job mix, it was also expansive, failed the test. But when we used a 40% slag with the job mix of Victor, it was clearly well below the threshold of 0.02%. And it passed the test. So this is sort of a case study of how we could potentially use this MCPT to evaluate job mixtures, right? So basically the summary of findings from this study is that MCPT is an effective short-term test. It's a 56-day test in evaluating ASR mitigation potential based on their composition and dosage levels. Like I said, if we can use a modified MCPT, especially matching the soak solution with the pore solution concentrations, along with the mix design or the mixture proportions of the field concrete, it has the potential to capture the influence of job mix parameters on ASR-induced expansion. That's our ultimate goal. And if you compare that job mix expansion to a control mix expansion, you can then figure out a % reduction in expansion that can potentially serve as a performance measure for ASR potential of a job mixture or its mitigation. There is, like I said, I didn't get to share here, but we also have some other work going on looking at more complex job mix formulations where you have multiple aggregates that are reacting, as well as SCMs that are releasing alkalis. I should also mention there is a lot of talk in these meetings about SCMs releasing alkalis and how they contribute to the alkali loading. My experience has been, yes, that is true. There are certainly certain SCMs that do that. One in case is sort of a glass-based type GS glasses, which I worked quite a bit with, and type GE glasses as well. But by and large, most SCMs are not, they don't fall in that category of alkali release type of SCMs. So I don't want everybody here to kind of go really berserk over the alkali release from these SCMs. Usually that is not the case, but you should be familiar with it. There are certain SCMs that do contribute that. But we're looking at implementing that as well in the MCPT, looking at how to model the pore solution compositions in those systems so we can match with the soak solution and apply to the job mixture. So with that, I'd like to just kind of leave you with the final thought that oftentimes ASR is sort of compared to cancer, and it's a cancer in concrete. But I do sincerely believe that it is a very preventable disease with effective testing. And I think more and more, as you saw, there are a number of test methods that are being developed, including MCPT. And I believe we are now at least have ways to deal with this battle, this issue, and come up with some reasonable answers in a fairly short duration of time. I know short is never short. We're always wanting to do it like today, but 56 days, that's about 8 weeks for MCPT. I believe is much shorter than 2 years with Concrete Prism Test or long. So with that, I'd like to conclude and take any questions.